I am R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we will discuss the topic on scalar and vector magnetic potential for the unit magnetostatics. And in electrostatics, it is seen that there exists a scalar vector potential and it is denoted by V. This is related with electric field intensity as E is equal to negative gradient of V. And in the case of magnetic field, there are two types of potentials. One is known as scalar magnetic potential denoted by Vm, and another one is vector magnetic potential denoted by A vector. So the scalar and vector magnetic potentials are defined with two vector identities, and they are obtained from the properties of curl as del cross del V is equal to 0. Here V is the vector, the potential, scalar potential, and del cross A is equal to 0. Here this A is the vector. So every scalar V and every vector A must satisfy these two relations. So considering Vm is scalar magnetic potential, then it must satisfy the previous equation del cross del Vm is equal to 0. But the scalar magnetic potential is related to the magnetic field intensity by the relation H vector is equal to minus del Vm. So by using this equation of 3, we can replace del Vm by minus H, the negative of magnetic field intensity. We get the equation as del cross minus H is equal to 0, or we can write del cross H is equal to 0. But we know that according to the Maxwell's equation, the curl of magnetic field equal to current density, that is del cross H is equal to J. So according to equation number 5, since del cross H is equal to 0, this J is also 0. The scalar magnetic potential Vm can be defined for source free region J, that is the current density is 0, H vector is equal to minus del Vm, and this is only for source free region where J is equal to 0. So similar to the relation between the electric field and the electric scalar potential, the magnetic scalar potential can be expressed in terms of the magnetic field H as V of m comma b is equal to minus integral of b to a H dot dl over a specified path. It is known that for monopole of magnetic field is non-existing, we can write the integral over the closed surface b dot ds equal to 0. Using divergence theorem, this integral over the closed surface b dot ds equal to volume integral of del dot b dv is equal to 0. So this del dot b is equal to 0 and b is equal to mu naught h, and del dot mu naught h is equal to 0. But this mu naught is not equal to 0 because it is absolute permittivity. It has the value 4 pi into 10 power minus 7 henries per meter. So del cross h can be 0, and h is replaced by negative gradient of Vm, that is minus del Vm. We can write the equation as del dot minus del Vm equal to 0, and so this is del squared Vm equal to 0 for source free region J is equal to 0. So this del squared Vm is equal to 0 is called as Laplace equation for scalar magnetic potential, and this is similar to Laplace equation for scalar electric potential del squared V is equal to 0. And now the vector magnetic potential. So the vector magnetic potential is denoted by the letter A vector and is measured in Webers per meter, and it has to satisfy the equation and where the divergence of a curl of a vector is always 0. So by writing del dot of del cross A is equal to 0, we know that the curl of A vector potential is equal to B, magnetic flux density. So del dot B is equal to 0. This B is equal to del cross A. The curl of vector magnetic potential for flux density is Del cross H is equal to J, and replacing H as B by mu naught, we get del cross of B by mu naught is equal to J. And now del cross B is equal to mu naught into J, and since substituting B as del cross A, we can modify the previous equation as del cross A is equal to mu naught J. And using a vector identity to express the left hand side as del cross A is equal to del into del dot A minus del squared A. So by substituting, we can equate this equal to mu naught J. So finally we can write the expression for J as 1 by mu naught del cross A r is equal to 1 by mu naught del into del dot A minus del squared A. Thus, if vector magnetic potential is known from current density J can be obtained. So, for determining A vector, the magnetic vector potential, the current density need not to be 0. In vector algebra, a vector can be fully defined if its curl and divergence is defined. For a vector magnetic potential A, its curl is defined as del cross A is equal to B, which is known. So, to completely define the magnetic vector potential A vector, its divergence must be known, assuming del dot A vector, and the divergence of A is 0, and this is consistent with some other conditions to be studied later in time varying magnetic fields. So, J is equal to 1 by mu naught into minus del squared A, or rearranging the equation, del squared A is equal to minus mu naught J. So, this equation is called as Poisson's equations for magnetic fields. So, now the vector magnetic potential due to differential current element, it is A vector is equal to integral of phi over the closed surface mu naught I dl vector by 4 pi r Weber per meter. And when this is replaced by kds for the distributed current element, so here k is the current density. So we can write the equation as A vector is integral over this closed surface mu naught kds by 4 pi r Weber per meter. And for volume integral, it is integral over the closed volume mu naught j dv by 4 pi r Weber per meter. So we can finally noted that the zero reference for the magnetic vector potential is at infinite. No finite current can produce the contributions as r is equal to infinity. So now the assessment questions, the types of magnetic potential, we know scalar and vector magnetic potential, Laplace equation and Poisson's equations of magnetic potential and field we have known from the PowerPoint presentation.